computing, working as a research scientist there. Right. So first, I kind of review what parametric gates are, because this is the basis for parametric resonance gates. Effectively, it's a flavor of what parametric gates are. And I'll go ahead and show you some data on the implementation of these parametric gates on a particular tunable architecture, where we benchmarked iSWAP and CZ with process tomography, and discuss a little bit about what the error budget for this gates. And in the second part of the talk, this is probably not published yet, but some recent result on benchmarking of these gates on tunable architecture using randomized benchmarking. We introduced very simple and scalable calibration of iSWAP. Usually iSWAP is a little bit tricky to calibrate than a CZ because of some time-dependent phase problem. And yeah, I will show you some data on very recent data on iSWAP and CZ on two floating tunable architectures that we published recently, so which we call symmetric and asymmetric configurations. So parametric gates, if you have two coupled qubits, there are several ways to activate entangling gates. One way is to activate the gate parametrically, meaning you kind of send in a modulated RF pulse, usually a few hundred megahertz in frequency, to activate the gates between them. So the qubits can be detuned. You don't have to bring them in resonance, but it could be detuned by 400, 500 megahertz. But by sending in a modulated flux pulse at the frequency difference between the two qubits, you can activate what we call parametric gates. So what are the pros and cons of these gates? In terms of pros, as I will show in the coming slides, the flexibility in operating points. So depending on the modulation amplitude of the pulse you are sending in, you can choose for every modulation amplitude a different modulation frequency. So you have in one period of flux quantum, you can have many operating points. So you can select the operating point that maximizes the fidelity, avoids collision between different resonances. So that has that selectivity, flexibility. The other is, I would say, you can easily construct is what we call native gates. Typically, the capacitively coupled qubits in superconducting architectures, for example, iSWAP and the CZ, a C phase, and an XY family with this parameterized gate. That's like a exchange interaction type gate. How about the cones? So because we have to modulate the qubit, at least one of the qubits, then we are introducing extra noise to the system. So the flux signals have two components. One is the DC component that allows us to park the qubit at its flux intensity point, usually at Fmax, the maximum frequency of the qubit. And we also send AC signal that also introduces extra noise on top of the DC. If you compare it with a fast DC gate, what the Google people or Decalo and others are implementing, they just use fast DC pulse. They don't use modulated pulse. In that case, what they have is just one source corresponding to a DC. They don't have extra noise channel in that case. What we have seen is, because of that, during this modulation, the T2 of the qubit decreases substantially. So we came up with some idea kind of to operate a particular point, what we call the AC sweet spot. Under modulation, the gradient of the frequency band, the average frequency, is 0 at a particular modulation amplitude. That at that point, actually, the T2 of the qubit resurges to what it was at the DC flux bands. So that's kind of one operating point we found, which really minimizes this flux noise. The other effect of modulation is a reduction of the qubit-qubit coupling. So if you notice the gate time for our parametric gates, of the order of 100 to 300 nanosecond, this is because of the modulation, the coupling is renormalized by a factor of 0.6 out of 1. So that means we are losing 40% of the coupling because of the modulation itself. So we said, okay, we have to come up with something. We cannot just lose almost 50% of the coupling and get a longer gate time, because that is it has implication on the fidelity of the gate. So I mean, there are many papers on this area since 2016, but we kind of pushed it to the next level and implemented this gate. So now coming back to, it's important to understand what we call sideband parametric gates as we know it, to understand what is a parametric resonance gate. So consider two coupled qubits, one fixed qubit, just a single junction qubit, and another a tunable qubit with two junction qubit. So you can send in a flux bias through the loop, and then modulate that flux, and then that flux modulation induces modulation in the qubit frequency. In principle, we are actually modulating flux we are sending to the qubit, which, because the frequency depends on the flux, you'll see a modulation in the qubit frequency. So if you look at the interaction Hamiltonian in the interaction picture, what you end up getting is something like this. So the 0-1 interaction between the qubit, 0-1-1-0 interaction, and the 1-1 and 0-2, higher levels, 2-0 on 1-1 interaction. Now look at carefully what the exponential terms in this Hamiltonian. If I look at the 0-1-1-0 interaction, that's the interaction Hamiltonian for activating iSWAP. So to enact this gate or this interaction, what I have to do is the resonance condition has to be met. So meaning the modulation frequency of the flux times twice n, where n is integer, minus the detuning has to be 0. For example, this can be kind of expanded in this way. The detuning here is just the average frequency, over a period, minus this twice the number of the number of sidebands equals to the frequency of the second qubit. So in effect, if you look at in terms of sideband physics, when you modulate a qubit, it kind of has this oscillation at it has so many frequency content. If you look at in the frequency space, what you see is sideband around the center frequency, right? This is literally the average frequency during modulation. So when we say a sideband gate or the standard parametric gate we implemented, we were using the first sideband where we kind of bring, in a way, in resonance, the first sideband, which is literally this frequency here, equals to the frequency of the second qubit. And instead of bringing the two qubit frequency in resonance, what we are doing is we're bringing the sideband frequency of the modulated qubit with the frequency of the other. So as you can see, the heights of these sidebands, kind of the weights, vary depending on the sideband you use. So for this kind of sideband, n equals to sideband or plus or minus 1, this renormalization factor is a kind of roughly a Basel function of the first kind. It's of the order of like 60%. So that's why we kind of lost this, 6%, 40% of the coupling. Now, the same is true for CZs. We have to meet these conditions. So the sideband has to match with the 1 to 2 transition of the other qubit, and so on. Now, how do we activate the parametric resonance gate? So instead of using sidebands, if we use the main resonance, literally the average frequency of the qubit, we can activate this gate. So, for example, here I'm showing the average frequency of the one of the qubit, usually the higher frequency qubit, and this black line shows the frequency of the other qubits, the unmodulated qubit. So this is the F01, and this is the F12 transition. So whenever the average frequency of the qubit matches with the F01 transition of the other qubit, when you bring them into resonance, you get iSWAP. And when you bring that the same F01 transition, the modulated one, with the 1-2 transition of the other qubit, you get a CZ gate, right? So one of the advantages of this is if you choose the frequency of the qubit to be close to each other of the order of 100 megahertz, what happens is the weight for the center band is almost 1. So that means recovering the bare qubit-qubit coupling. The other advantage of this is that I can choose any modulation frequency. So the average frequency is just taking the period of the average frequency over time, taking the average frequency of the qubit over a period does not depend on the modulation frequency. So I can use any modulation frequency I want to avoid any collision around that resonance. So, it's very easy to activate the gate. So this is kind of the main idea of this. So first, it gives me back the bare coupling from design, no reduction. Second, flexibility in choosing the frequency of modulation of the flux pulse. Okay, so first, we kind of have to verify this. Is there any reduction in the coupling? Or, are we getting back the bare coupling we designed for? So we implemented this idea on a tunable coupler architecture using this grounded coupler. So look at this. This is the device we used. So we have this qubit on the left, the red one, qubit on the right, the green one, coupled via this tunable coupler, just a single pad, meaning, the junction is grounded, connected to the ground. That's why we call it ground. But for this qubit, they are floating because the junction is floating between the two pads of the qubit, the transmon qubit. So what we have is, each qubit is coupled to readout on the feed line, and including the tunable coupler. There is RF control for running, single qubit gates for each qubit, and there is a flux control for the qubits as well as the tunable coupler, because we have to move the tunable coupler to get the coupling we need. So the idea of this tunable coupler, as reported in many papers by now, is we can cancel the qubit-qubit coupling when we don't run the gate, when it is idle. So that's very important. This is what the original paper from Will Oliver 2018 proposed. And, Google people have implemented it, and others also implemented this. So it allows us to park the qubit where G between them is 0, or the coupling between them is 0. So this is exactly what we implemented. So now the point is, now we want to check whether the coupling we get is from the bare coupling. So the first thing we did is without modulation, of course, the baseline measurement. So what we did is we send in a pi pulse on the first qubit, and then send in a flux pulse. This is a fast flux, no frequency content, on the second qubit, so that to bring them in resonance. That's how we measure G, so that they exchange energy. At the same time, we are changing the flux paths on the coupler such that you can, tune the coupling between them. So the coupling between them has two components. First is the direct coupling between them, some capacitive constant coupling. The other is the coupler mediated effective coupling, which depends on the frequency of the coupler. So by moving the flux path, effectively moving the frequency of the qubit, you can make the coupling stronger, 0, or positive or negative, whatever. So you can control the coupling. So that's why we're sending this flux pulse, and very effectively that amplitude says that we can measure the coupling as a function of that flux path, or that's function of the coupler frequency. As you can see here, the red dots are the measurement from the fast DC measurement, showing that the coupling decreases around F max, where here the frequency of the coupler is above the qubit. So when the coupler is away from the qubit, the coupling becomes smaller and smaller. It happens that for this particular device, the coupling is almost zero around F max when the coupler is at its maximum frequency. And then it gradually increases to maximum frequency as you push it down to the qubit. And for the next measurement under modulation, we do the same experiment but replace the flux pulse on the qubit 2 with a modulated flux pulse, right? So that means now this is kind of emulating how we activate the gate. That instead of bringing the qubit with a fast flux pulse, but we bring the qubit by modulating one of the qubits, effectively the average frequency matching the other frequency of the qubit. So the same experiment, as you can see, the green dot shows almost the same coupling as the Baire coupling. So confirming our prediction, our theory that we can recover the coupling between them, the Baire coupling between them. So we also calculate the renormalization factor I was discussing about. So remember the G effective under modulation is renormalized by the Bessel function, so which is approximately 1. So this is exactly what we expected. All right, so now how do we find the operating parameters of the gates? So the first thing you have to do is measure the qubit frequencies. Once you got the measurement, the frequency of the qubit and then the anharmonicity, because that's important, especially for activating CZ. So you kind of plot, take the average frequency of the first qubit Q1 and plot it as a function of the modulation amplitude. Remember that the flux expression. So the AC amplitude. So if you plot that, you'll see, and then put the frequency of the other qubit here, you see that when the average frequency of the modulated qubit is the same as the unmodulated qubit, you have iSWAP and a CZ. So what's important here is you need to know at what amplitude of modulation the qubits become resonant to each other. And the same thing for a CZ. So that's kind of one of the parameters for the gate. But the other way, to do it is, so yeah, I was kind of saying that the interaction for iSWAP is swapping energy between 0 and 1. For CZ, you can do it two different ways. One is, interacting between 1, 1 and 2, 0, literally this gate. Or if the other qubit is modulated, tunable, you can modulate even the other qubit to activate this gate. This, this gate, 1, 1 with 0, 2. So it has some flexibility, you don't have to modulate only one of the qubit to do it. So you can also modulate the other qubit to do it. But you cannot get iSWAP from that, but you can get CZ. The other way kind of to look at is if you plot the resonance conditions that I showed you in that Hamiltonian. So the conditions I'm repeating them here for iSWAP, the average frequency for parametric resonance gate, the average frequency has to be, sorry, I made a mistake here. It has to be divided by 2. It has to be divided by 2. I'm using the first sideband. So everything has to be divided by 2 because it's just because we are parking it at F max. Anyway, so if you plot this resonance condition, what you see is, every point here, for example, can activate iSWAP. You just select the modulation amplitude and you have to choose a particular modulation frequency, you can activate iSWAP. But for parametric resonance gate, it corresponds to 0 frequency. Remember, we are bringing the qubit to resonance for the case of parametric resonance gate. That's why we call it parametric resonance gate. So this detuning becomes 0, right? So exactly that corresponds to the the parametric resonance gate. So the reason I showed this plot is because what modulation frequency should I choose for activating a parametric resonance gate? I said it doesn't depend, right? So, but the problem is if I choose, for example, this frequency here, it would collide with the other resonances, the sideband gates. So it's going to mess up my gate. So kind of the rule of thumb is to choose any frequency above these resonances. So for example, for this particular operating point, I can choose more than 200 megahertz modulation frequency. For a CZ, somewhere around 250 or more. Because we don't want to choose below, because there are other resonances, the higher harmonics, then you will see you can get easily some collisions. So these are, how we pick the modulation frequency for activating this parametric resonance gate. Now, once you have these parameters, so remember I have showed you this coupling versus flux bias plot. So you want to pick, the fastest gate, or the gate that gives you the gate time that gives you the optimal fidelity. So you kind of choose that fast flux amplitude for the coupler, right? You park it somewhere, you bring it to with some flux bias or frequency of the coupler, and you bring it back. So you have that parameter, the coupler flux bias, and then identify the modulation frequency. We did identify, and then run a chevron measurement, meaning you send in, for example, a pi pulse 1 qubit modulate. This is exactly what we had to measure G, but you should now literally to get that measurement data. I was literally running a chevron measurement like this for every point, and fitting the data and backing out what the rate of oscillation is. That is kind of G. So as you can see here, this is the modulation amplitude on the qubit, on qubit 2. So literally, I'm bringing from its parked bias to the bias of around 140 milliamps or 0.145 knot to bring the qubit to resonance. So this is the resonance condition right at the center. So where you see the swapping of population between the two qubits. So to pick the gate time, it's half. It's not a full rotation for iSWAP. It's half rotation. So it's like about 44 nanoseconds for this particular interaction. So one thing I want to stress is, you might ask, why not just use fast flux pulse? Why you guys modulate this? So one of the advantages of using modulated pulse is you don't have to deal with this pulse distortion. So if you have to kind of pre-compensate the distortion, you have to measure the transfer function and so on, to make sure that the pulse that you send is actually not distorted when you reach to the fridge, down to the qubit. So here, we didn't do any distortion. It's in particular on the qubit signal. On the coupler signal, yeah, we are still using DC pulse. We could see some distortion, but what really matters most is the qubit when you have a population transfer between. So yeah, this is really one of the advantages of a parametric resonance gate. So yeah, we pick iSWAP and we benchmark this gate with process tomography, kind of compensated because this measurement does depend on the readout fidelity. So we kind of compensated the readout error and applied some positivity constraint, complete positivity constraint. And what we found from this process tomography measurement is we can get 99.3% fidelity for iSWAP. And we also compared this iSWAP process matrix with the FC. So the FC in a unitary is something like this. So if there is any error on the swap angle theta and the conditional phase pi, this will kind of tell you, oh, probably you don't have full population transfer, so the angle is not exactly pi over 2, or the iSWAP you expect to be pi over 2. So there may be some unoptimized population transfer. And if there is a leakage or ZZ dynamical ZZ error, you might see some conditional phase as well. So from here, as you can see, it's almost pi over 2 here, and the conditional phase is also very little. So, but you might ask what would be the limiting factor for the fidelity. given the gate is fast, and our T1 and T2s, sorry, our T1s are really good, 60, 80 microsecond range, but the T2s are not that great. But this is, remember, the T2, one of the qubit is modulated, so there is a decrease in T2 because we are not at Fmax, at the sweet spot. Every time you go away from the sweet spot, the T2 drops because the noise is proportional to the gradient of that band. The higher the slope, the shorter T2. So when you are away from Fmax, the slope becomes larger and larger. In any case, for this gate time, the process fidelity, due to incoherent error, is about 99.67%. So no, phase errors, but it's largely limited by incoherent errors. Short T2 specifically for the modulated qubit. So we also run CZ, as I've showed you here, again modulating the same qubit. So we can activate two gates on the same edge. So this is kind of advantageous when you run some circuits simulation. So here the gate is a little bit longer, about 124 nanosecond. We didn't really optimize, honestly, but this is what we found. So the CZ of 97.9%. So when we compare it with FC, again, it kind of tells you what the phase error would be, right? So we got, the conditional phase supposed to be a pi for a CZ, right? And we are getting like 2.8, which is substantially different from pi. So indicating that there is, when you apply CZ gate, what you do is you see interaction between 1, 1 and 0, 2. So there could be some strong ZZ coupling during that interaction, inducing these phase errors. If you look at, the coherence limit, from measured T1 and T2, it's 98.7. So which is really far from what we measured. So, again, for CZ, the fidelity is largely limited by the phase error as opposed to coherence time. So, I mean, the advantage of one of the things that could improve this is using optimal control. I think Felix and others have this nice paper from 2017 where we can use that method. So even Will Oliver has. No worries, no worries. Yeah, so it's a nice idea. This optimal control can reduce this easy error. There are some other methods like dynamic decoupling, which kind of reduces or eliminates easy error. Now I'll move to a second part of the talk, benchmarking of iSWAP and CZ with randomized benchmarking. So what I've showed so far is just one gate. So when you run, circuit simulation, you might have some, you have some depth of gates, right? Meaning you have to repeat this iSWAP many, many times or CZ many, many times. You have to make sure that these gates are repeatable. If they are not repeatable, they are not gates, they are just interactions, right? So one way to kind of validate if the gate is repeatable is to use randomized benchmark. It's a very nice tool, at least for 2 qubits. So one of the things that I would like to kind of bring to your attention is when you have a CZ gate, there is no energy interaction. You start with the state, you end up with the state. So, 0, 0, nothing happens, 1, 0, nothing happens, 0, 1, nothing happens, but 1, 1, it becomes 1, 1 with a phase shift, right? So you still stay in the same state. There is no energy exchange. So you don't have to kind of make sure that the frames of the qubit relative to Earth changing. So no frame tracking. So we can just apply, if the local phases, like apply on the microwave pulse, and I will discuss more on this, but you can use what we call virtual phase correction, meaning you update the RF pulse with the appropriate phase you measured from tomography. But for iSWAP, it's a little bit tricky because you start with, say, 1, 0, you end up with 1, 0, 1. You swap in the population, right? So that means you have to track the frames of the qubit relative to each other, because you are swapping with this energy, and the phases are changing with time, as I will show in the next slide. So it's important we track the frames of the qubit. Yeah, and the other aspect is RGs does not commit with iSWAP. So it's important we kind of track these phases and apply them after each iSWAP. Because I cannot apply, after two iSWAP, I can apply these RGs. No, you have to apply the RGs after each iSWAP because they don't commit. So to kind of give you a little bit more detail, these things that I mentioned, the time-dependent phases. So if you consider like the free Hamiltonian of the qubit, two coupled qubits, you have this, if you start with some wave function, it evolves, the wave function evolves like this. And in the last frame, nothing happens, right? So there is no really, you end up getting to the original states in the last frame if you go to doubly rotating frame. Now, if you have this interaction, the iSWAP interaction, for example, so this is the interaction Hamiltonian in the interaction frame, then what you end up getting is a swapping, that's what I was saying, swapping of the population, right? So you start with, this initial state, say you kind of evolve with the free Hamiltonian, the first part, and then you apply iSWAP, and what you end up getting is a swapping of this, population with some phase. So if you go to the, doubly rotating frame, effectively, transforming the Hamiltonian to this interaction, what you see is these time-dependent phases, which depends on the detuning between the qubits. So the first point here is these states 0, 1, and 1, 0 acquire these time-dependent phases, or local phases, I would say, after the application of iSWAP. And we have to track it, because if I apply a gate after a later time, I cannot use the phase that I calibrated now, because the phase will be different already there. So I have to track that phase and then apply it right at the right time. So it's important to do this calibration. So I will say a little bit about what other people thought about this. So once you get those phase measured, so you can still use the virtual Z's, meaning you just update the RF pulses with the appropriate phases of the qubit. So what other people, specifically Will Oliver, did in this recent paper is, instead of using a virtual Z, they use actual RF pulse. So they constructed what they call this Euler Z pulse. So it's made of three RF pulses, x minus x over 2. This is the arbitrary angle, because you need arbitrary angle, because you don't know a priori what phase you need for the correction. So they have to calibrate. If I want, say, I don't know, 1/3 of radian, then I have to make sure what amplitude of Y I should send to generate that correcting pulse. So what they do is you apply swap, then you have to apply these Euler Z's at the end. It could apply from the beginning, but you can apply it at the end with appropriate phase. So they constructed this, as you can see. Yeah, it does work. We tried it, but it's not scalable. First of all, it induces, error, because these gates themselves are not perfect, right? They have their own error. So when you apply them, you're inducing error to the gate. And the other thing is you're increasing the gate time. So let's say each X pulse is 60 nanosecond. So 180 nanosecond on top of the iSWAP gate time, right? So you're kind of increasing the gate time. So that that has implication in terms of incoherent errors, because if your T1 is short, if your gate time is long, you kind of induce some incoherent errors to the gate. So the other thing they did is to cancel that dependent phase, they have to bring the qubit in resonance. So when they do that, there will be a microwave crosstalk. So they implemented this crosstalk correction method. So that's why it's not scalable, I say. Yeah, it's a nice idea, but when you have a larger chip like ours, it's just not scalable. You cannot just send in microwave pulse where the qubits are in resonance. All right, so the need for frame tracking. So that's what I alluded to. So we have to track the frames of the qubit because of the time-dependent phases. So how do we measure them? We run a tomography measurement. Just a single tomographic measurement is enough. So what we do is we kind of prepare 10 different initial states out of, it could be pi pulse on each one, pi over 2, pi over 2, and some combination of those to kind of get what the iSWAP is doing to different, initial states. So what we do is we measure this iSWAP tomography for iSWAP. So this is the first measurement you get. As you can see, there are some local phase errors. I should have showed you the ideal process matrix. You can imagine it's just close to this. But if you go back and see, oh, there is some phase errors around some of these pixels. So what we did is we updated the frame, the RF pulses with appropriate phases. So when you run the tomography, you construct these process metrics. So you calculate the phase that maximizes the fidelity by comparing it with the ideal matrix, right? And then you end up getting what local phases you need to get that maximum fidelity. This is what those numbers mean. Then you update the RF pulses with these phases just once, and you get this. Yeah, it works. It corrected the phases. But the question is this repeatable? If I say apply iSWAP and its inverse, would I get identity, for example? So this is what, okay, maybe before I go that, so this is what, I was talking about. The main idea is, repeatability of the gate. So we need to track the time dependence to ensure the same gate is affected no matter when in the pulse sequence. You have to say you are running some circuit. So you apply one here and at later time another iSWAP. In that sequence, whenever it is applied, it should be repeated. So no matter what I apply, the gate is repeatable. So that's very important. So one of the things we have at Rigetti is we have this in-home built electronics for generating these pulses. So they have these what they call numerically controlled oscillators, NECOs. Probably people work on the electronics know well. It allows you to track frames or phases on each qubit. So each card, the RF card, comes with these NECOs. So you can track, it has its own code. So it tracks the frames of that particular qubit. So again, if you have, for example, in the middle of the circuit, there is some time-dependent phase on qubit 1, time-dependent phase in qubit 2, you apply your iSWAP. The iSWAP, what it does, it switches some of the phases. So with some constant, if there is some another constant phase incur in the system, you can get some additional phase. But once you get these phases, what you do is remember that the time-dependent phase, the detuning between those. So you take those two phases and subtract them. So like for the first qubit, phi1 minus phi2, for the second qubit, phi2 minus phi1, that will be the phase correction you have to apply on the RF tones. So once you do that, that's it. You just need to do it one tomography measurement. That would be enough to kind of as a calibration for iSWAP. So to kind of verify this, as I was saying, is okay, let's apply an iSWAP, get the phases measured, and then make sure it's corrected the phases and close to identity. Sorry, close to the ideal process tomography for iSWAP, and then apply iSWAP, and then after that, inverse of iSWAP. Inverse of iSWAP is nothing but because it's really hard to construct iSWAP using a real pulse. It's inverse of iSWAP using a real pulse. It requires some kind of tricks, but the easy way to do is just you apply iSWAP and then again virtual rotation on both qubits with a pi. That gives exactly inverse of iSWAP. In any case, so we get what we expect is very close to identity. Yeah, there are a little bit of phase. Maybe the optimal quadrature have moved a bit. Maybe the phase correction are not perfect, but very little phase. But this is very close to identity, just limited by the fidelity of iSWAP itself. So the fidelity of this iSWAP would be roughly the fidelity of iSWAP square, right? So if it's 90%, 90% square, or 0.9 square would be the fidelity of this. So this is what we found. Now, this is 2 gates. Of course, it's a good thing to see, but what we want to see is randomized benchmark. So just for those people who probably not familiar with randomized benchmarking, and a randomized benchmarking measurement, what we do is we start with a ground state on both qubits, and we select this Clifford group for 2 qubit gates, is about 11,000 of them. Okay, so we apply those gates many times, and then we apply what we call a recovery gate, meaning since it's a group, the Clifford is a group, you can find a Clifford that would undo everything that you applied. So what that means, it brings you back to the ground state. What we measure at the end is how good is the ground state. So this is what the standard, what we call reference RB is. And the other is, if you want to characterize a particular gate, you have to interleave these iSWAPs with the arbitrary Clifford you generate. You pick from those Clifford groups, and then apply again the recovery gate. So from these 2 measurements, you can back out what would be the performance of that interleaved gate. For example, in this case, iSWAP. So this is what we did. The RB, the reference RB is 98%, and the interleaved RB for this iSWAP, this is literally the iSWAP fidelity, is 99.4%. So this is really nice. So this is for about 44 nanosecond. Sorry, not for 52 nanosecond gain. But this just checks that it works. The calibration works for iSWAP. We actually implemented this. It's not just necessarily for modulated pulse, but also for fast flux pulse that I was referring to earlier, like the Google group or the Carlo group does. You can also use that calibration method for running fast DC gate. We can do that. So you can see that, again, this is not optimized gate. We're just checking whether this method works or not. It does work. As you can see, is I can get repeatable iSWAP. Other factors that, so there are other things we have to worry about, making sure that when you generate the pulse, we have to make sure they are aligned. So if they are not aligned, I thought I'm applying a gate, but I send an RF, but the flux pulse is applied way later than that. So it messes up my gate. So we have to make sure that the gates are aligned. And the other thing is always there is a tail because of some transfer function. At the tail of the pulse could be a little longer. So you have to wait, a few nanoseconds to make sure that the pulse amplitude is 0. So that's the kind of things we have to do. So we implemented this. I'm not going to describe this floating tunable coupler, but we implemented this on a tunable coupler architecture. Symmetric means the pads are symmetrically coupled to the qubit pads. Asymmetric means the 2 pads of a tunable coupler not coupled symmetrically to the qubits. This has implication in the polarity of the coupling, the G12 and the G1C and G2C. So if the polarity of this change, then you have to make sure what the frequency of the coupler with respect to the qubit is. So because that also changes the sign, right? So it's just an interplay between the polarity of the coupling and the operation frequency of the coupler. In a symmetric case, we have to go above the qubit frequency for the tunable coupler to get the G equal to 0 point. For the symmetric coupler case, we have to operate below the qubit frequencies to get the G equal to 0 point. Okay, probably I will skip this. So we kind of validated this, that the G equal to 0 happens for the symmetric case below. This is the qubit frequency here, below the qubit frequency. So this is like the F max of the tunable coupler. So G equal to 0 definitely happens below the qubits. And for asymmetric case, the G equal to 0 happens when the coupler is above. This, again, is a confirmation of theory we report in our paper. Probably the points that we measured here are fatal to this function because there is a flux dependence that I haven't seen in papers. It's very important to add the flux dependence of the coupling between the qubit and the coupler, which is really important. Okay, so we implemented iSWAP on this gate. Okay. Oh, I'm aware. Can you give me 5 minutes or so? I'll be done. All right. So for symmetric coupler, again, we kind of plot this resonance plot to make sure where the gate operating points are and run a chevron measurement to get the gate time, the amplitude that needed to bring the qubit in resonance. So these are kind of the parameters. That's DC parking point where G is 0, fast flux amplitude where you want the gate time to be, kind of determines what the gate time would be. And the condition for resonance around 19 milliamps, modulation frequency well above the other resonance, the sideband resonances, so it is safe. So once you pick that, you run again that calibration method. First, tomography measurement, update the phases, make sure that it works, and then run this double iSWAP or 2 iSWAPs in a row, and make sure that it works. Again, we run this for many hours, about 6 hours, and you see that the gate is very stable. And if you see the CDF of these points, in 70% of the time, we are getting more than 99%. So this is really great to see. So we were kind of trying to explain, there is a little bit of variation if there is any correlation with T1, because we know T1 varies with time. So as you can see here, T1 versus the fidelity measured, we try to find any correlation using what we call the Pearson correlation coefficient. It is nothing there. So there is no correlation at all. So the fidelity is not limited, limited by T1 in a way. We do know that, we measured the T2 under modulation. This is how it looks like. Initially at F max is about 16 microseconds. But at the operating point, it's already about 6 microsecond T2. That's what I was talking about, the dephasing under modulation hertz. So that's literally the limiting factor here to 99.4% fidelity. So we do know that our gate fidelity is limited by the T2 under modulation of the qubit. We also run CZ on the same pair, just picking up the resonance condition here, and we got 98% CZ. This is because, again, the T2 is nowhere far away from F max, so it is about, I would say, 4 microsecond T2 around where we operate the CZ. So yeah, the fidelity again is limited by T2 under modulation. So we did also the same thing for symmetric tunable coupler. Again, you park it here. Either you go there to get higher G, or you can go to F max of the tunable coupler and come back. That's how we operate and run CZ the same way. It's about 14 nanosecond iSWAP. again, you can repeatedly get 99% fidelity. So this is kind of the TDF of this gate. It's very distant, stable gate. Again, this is 10 microsecond under modulation. The gates are limited by T2, which is what we expect. Yeah, the same thing for CZ. Here, we were able to get more than 99% gate, and over time, we saw some variation, but still, we get 45% of the gate more than 99%. So, I mean, the method works, really. This is really nice to see. Yeah, this is my message. Yeah, we demonstrated high fidelity parametric resonance iSWAP and CZ gate on tunable coupler architectures. Showed that parametric resonance does not rely on the frequency of modulation, providing flexibility in avoiding collisions. And yeah, we introduced a very simple and scalable calibration of iSWAP. Thank you for your attention. And I would like to thank my colleagues at Rigetti for their contribution to this.
Thank you so much. So that was the scheduled time for our talk. And so now the floor is open for questions and informal discussions. Yeah, do we have questions already before I start my questions? If not, I'll ask one already. So you showed two gate times, right? Around 44 nanosecond and the 120 nanosecond.
Yes.
So according to you, are these fast, or are you guys already working on faster implementations, or you are already working on optimizing these?
Yeah, so the 121 is just because honestly, we didn't have time and the device doesn't work anymore, really optimizing. But the CZs that I showed on recent devices is less than 60 nanosecond on both iSWAP. iSWAP even 40, even 32 nanosecond. So we do work. So the thing is, when you go shorter gate time, you have to worry about leakage to the coupler, leakage to the higher energy levels of the qubit. So you would have to play with optimal pulse shape on the coupler itself. So yeah, we are pushing to go lower than 30 nanosecond gate time, but we haven't played the optimal control part of it.
Right. So on the same line, so I think the nearest competition that comes to this gate are the fixed fast flux bias ones, right?
Yes.
So where do you put these numbers in comparison to numbers from there? Like, do we have physical implementation numbers for those, or we don't have
Yeah,
them
I
yet?
mean, for example, the fast flux iSWAP I showed you is, I don't remember, but a little faster, but
Mm-hmm.
of the same order. I
Okay.
would say the same order. We can push it to even less than 20 nanosecond, but the question is how good the fidelity will be.
Right. So
Yeah, but
talking about
of the order
fidel,
of 30 nanosecond
yeah,
is, you can comfortably get more than 99%.
yeah. So you are also mentioning scalability. Have you guys already faced challenges when, I don't know, implementing this on a 20 or 30 qubit chip, or is that not the case so far?
Good question. Yeah, so one of the things that comes with this kind of architecture is you have almost all qubits tunable. So you're sending flash signal to all qubits. So there is substantial crosstalk. So you say, okay, for this edge, I park it to G equals to 0 point. So you have to have sending some flux paths on the coupler to park where G equals to 0 is, right? Now, when you operate the other gate, because of crosstalk, that point could move. So we have to apply some compensating pulse on this tunable coupler to cancel, that drift from the G equals to 0 point. So yeah, there is some issues we have to deal with when we scale in terms of making sure that the parking points are not moving. when you operate gates simultaneously.
Right. So I think also related to that is the recalibration cycle that you showed. I think 6 hours or something that one of the
Yeah.
plots mentioned. So is that less
Yes.
or more when it comes to other gate implementations that Rigetti has right now?
Um, Usually we, on the deployed devices, we have a 4 hour window retune. So, I mean, it depends on from edge to edge, but I think it's maybe a little better than what we have in terms of stability.
Oh, okay. So seems like quite a bit of a positive side on this gate. So are you guys planning to have this deployed on one of the public, well, not public, but like
Uh,
production machines
uh,
or yeah.
yeah, uh, not currently, but in the near future.
Mhm. Okay, so do we have more questions from? Okay, I think Daniel has a question. He raised his hand.
Mhm.
Mhm.
Um, I think I didn't quite understand what it means to keep track. So you said you have to keep track of time when you run the iSWAP gate because of different resonance frequencies, I guess. Um, so at some point you will have an entangled state, right? So you have one state. There, you showed this 4x1 vector with different times. Um, so I don't. Yeah, can you explain again um, what you have to do with this state when you apply, let's say, a single qubit gate to one of the qubits or something?
Okay, so let's say we don't have this time dependent phase
Mhm.
for the case of CZ. So there is always the qubit is always evolving, right? Omega 1 times t with time,
Of course, yeah.
right? So that is the phase you track, but it's not swapping, it's not changing with the other qubit. So
Mhm.
for that, you know that phase, what, say at t equals to tau, you know what phase it will be accumulated, right?
Mhm.
So um, you just apply that. You know the frequency of the qubit. You know what time, because you have every card has its own clock, and then you apply the phase because you know everything. But this is on top of that. You have this additional phase because of the detuning, because of the swapping. There will be this detuning dependent phase.
Mhm.
So you have to. It is different for each one. So you see, one is plus, one is minus, right? So you have to track this phase as well. It's nothing. That's the only difference. So
Mhm.
if you don't track it, you don't have any. You cannot say, "Oh, I can apply omega 1 times t" at the end. It doesn't work.
Yeah, I see that there's that it's good to keep track of these times. I just don't understand how that how to treat it in an entangled state, I think. Yeah, okay. I don't know how to explain my question,
What
I
do you
think.
mean how to treat an entangled state? So this is the impact of the entanglement, right? When you apply iSWAP, you're kind of an entangling interaction, right?
Yeah.
So that is the impact. That's what is picking up from that interaction.
Okay, yeah.
You just have to know the phase of the each qubit
Mhm.
at all time.
Mhm.
You just know you cannot pre-calculate. Say, oh, uh, it's omega 1 t. I can apply it at the end.
Yeah. There's an
It's not the
additional
same.
phase.
Yeah, I mean, to me, it's like an additional phase you have to keep track of.
Mhm. It's just funny because it's a phase that depends on the component of the state vector, right?
Yes,
Yeah.
it does.
So then, so
But you are
okay.
applying on the lab frame. So, okay, maybe it's a little bit confusing. When we apply the phase correction, we
Mhm.
are applying in the lab frame. Everything is done in the lab frame. This is kind of
Mhm.
for us to understand how what to expect in the logical frame, right?
Okay,
But
yeah.
when I apply, each qubit has their own frame, right?
Mhm.
what I'm saying is, okay, when there is interaction like iSWAP, there will be an additional phase coming.
Okay.
So I have to add that phase on top of what I have before.
Yeah. Okay. That makes more sense. Thanks. Mm-hmm.
Our speaker for today, thank you so much for agreeing to present, and we got to know a lot about definitely a new kind of gate that seems very promising. So yeah, thank you once again, and hope to see you soon somewhere.
All right. Thank you so much for the invitation, and thank you for coming.
Bye bye.
Bye.